This next video is about the mechanical advantage of levers. The easy part about mechanical advantage, or ideal mechanical advantage about levers, is it doesn't matter which class you have. You use the exact same equation or formula for first, second, and third class levers, no matter what it is. What the equation is the distance to the input, which is u, divided by the distance to the output, which is the object you are moving. The distance, as it says, is measured from the fulcrum, which is very important to remember that you are measuring everything from the fulcrum, not from the end. So wherever the fulcrum is, that is your measurement. The one thing that is different about levers and its mechanical advantage is we have seen that with machines, or maybe you've noticed on some of your assignments that a lot of the machines have a mechanical advantage that is greater than 1. But with levers, you sometimes will get a mechanical advantage of exactly equal to 1, and sometimes you will get a mechanical advantage of less than 1. And we'll talk about what that means or the significance of that as when we get to the last video for this unit. And so that's what this last item says here, where it says the mechanical advantage can be any number. It can be less than 1, it can be greater than 1, or it can be 1. Okay. So if we look at some examples, the way that I abbreviate this is D in over D out. You have first class levers on the first example. And this one, with all the lever ones, I'm only doing, I believe I'm only doing ones where you calculate the IMA, just to kind of show you that it can be any variety of numbers. So on a first class lever, if we look at the first example, which is this one, the IMA is going to be the distance to the input, which is where your hands are, divided by the distance to the output. So in the example, first example, which is here, sorry, I have the IMA is equal to 15 meters divided by 5 meters, and I will get a mechanical advantage of 3. So if the input is farther away from the fulcrum than the output, you will get a mechanical advantage of greater than 1, which again means that it increases the force that it increases your force that you are applying. If I look at the example, the next example, the teeter-totter or seesaw, however you want to look at it, the two children or people on this one happen to be the same distance apart, so that when I do the mechanical advantage of this example, I have 2 meters over 2 meters, which is a mechanical advantage of 1. Now you might be wondering, why would you want a mechanical advantage of 1? If you have a mechanical advantage of 1, and this is true of levers and pulleys most of the time, in terms of frequency, it would be those two machines. That means that you are changing the direction of the force. So if you look at the example here of the first class lever, to make this person go up, this person had to apply a force down. And the same thing happens when you have a pulley, a single pulley that is mounted on a surface. If you, by pulling something up, you pull something up by pulling down on it, and sometimes just changing the direction is very useful. You can put your whole body weight into it, I guess is a good way to put it. And so first class levers, you will always get a mechanical advantage of, or with first class levers, you could get a mechanical advantage of greater than 1 or less than 1, because all you would be doing is shifting that board, the distance of the board, or the distance to the fulcrum. With a second class lever, the difference on this one is that whenever you have a second class lever, your mechanical advantage will always be greater than 1, because the input is way out here and the output is in between the fulcrum and the input, which means that you will always have a larger number on top and a smaller number on the bottom. Even if they are very close together, for it to be a second class lever, the input is farther away than the output. So in this example, I would have an IMA where use my equations to show you, good form. The input is 25 meters versus the output is 2 meters. So this one would have a mechanical advantage of 12.5. All second-class levers make it easier to do your work by increasing your force. All of them. If we have a third-class lever, this would be exactly the opposite, essentially, of a second-class lever. That you have the output way out here, so that your output is always the larger number, and the input is always a smaller number. If you think about what that means in terms of the math, you will always get a decimal, so a number less than 1, which means that a third-class lever actually decreases your force, which might seem odd, but if you think about the types of machines or the types of levers that are third class, sporting equipment, so hockey sticks, bats, lacrosse sticks, tennis rackets, things that are used for cleaning, so mops and brooms and rakes. The difference, or the reason you'd want to use a third class lever is, yes, I apply more force, so it makes my force smaller, but the trade-off is then the distance is longer. If you think about that, when you're using a broom, my hands move a shorter distance than the pile of dirt that I am moving. And so that is where the advantage comes with mechanical advantage of less than 1. So if I look at this particular example, my IMA is D in over D out. So I would have 2 meters over 25 meters, essentially the opposite of my example on the previous one. And I will get a mechanical advantage of 0.08. And so the point or the usefulness of a third class lever is that it increases the distance so that you use a smaller distance even though you have a greater force. And that is it for the mechanical advantage of levers.